So this video is part 2, section 1.3, and in this lesson, we are going to look at how to vertically or horizontally stretch or compress the graphs of the parent functions that you guys are familiar with. Another word, so I sometimes interchange these. Our textbook uses the word compress or compressing. You can also say shrink. I know Miss Walters says shrink. So compressing is also known as shrinking. And you can use either term for me. Okay, so we're going to look at vertically stretching and compressing parent functions first. So let f of x be a parent function. And if the parent function is being multiplied by a constant that is greater than 1, that's going to end up vertically stretching the graph. And that's because each of the y-coordinates ends up being multiplied by whatever that constant is. So if that constant is 2, 3, 4, 4.5, the y values are going to end up getting larger or end up being larger by whatever that factor is. So it will end up vertically stretching the graph. Now, if the parent function is being multiplied by a value that is between 0 and 1, then that's going to end up actually vertically compressing the graph of the parent function. So like multiplying the parent function by 1/2 or 2/3, that's going to end up actually shrinking the y-coordinates of the points of the parent function. So we say that the graph is vertically compressed or vertically shrunk. For the terminology, or whenever the verbiage to describe what's happening, here I'll do it for stretch first. We would say that f of x, so the parent function, f of x is vertically stretched by c. Okay, and that's if c is greater than 1. In the case of c being between 0 and 1, we would say that the parent function, or in this case, we're defining the parent function to be f of x, is vertically compressed or shrunk by c. And just like when we were talking about shifts, I want us to think back to kind of that most simple function, y equals to x. Remember, y equals to x is just a line that has a slope of 1, passes through the origin. So I'm graphing on here that line. And labeling. Okay, and we're talking about vertical stretch versus compression. So let's say that we have the equation y equals to 2x. And in a different color down here, I'll write the equation y equals to x over 2, which can also be written as 1/2 x. I just want to show you both ways, just as a reminder that if you see x over 2, that is the same thing as x times 1/2. Now, in this first equation, you guys know just from your knowledge from Algebra 1 that is a line that has a slope of 2 and a y-intercept of 0. But let's think about this from the transformation perspective. So our parent function being y equals to x, that 2 represents a vertical stretch by 2. And what that means for actually graphing is that we're going to multiply each y-coordinate of the parent function by 2 in order to have the same x as the parent function. So must multiply each y by 2. So the point 0, 0, if we multiply the y-coordinate there by 2, stays the same. The point 1, 1, though, when we multiply the y-coordinate by 2, ends up moving to 1, 2. The point 2, 2 would end up at 2, 4. So I'm just multiplying the y-coordinate for each point on the parent function by 2. So the point 4, 4 would end up being at 4, 8. 5, 5 would end up at 5, 10. And I'll end up going off the graph. And then like -1, -1 would end up at -1, -2. -2, -2 would end up at -2, -4. So you can think about stretching vertically stretching, oops, I was off on that one. Vertically stretching this graph by multiplying each y-coordinate from the parent function by 2. Oh, why didn't that straighten? There we go. Okay, and now for the equation that I have in green here, y equals to 1/2 x. The parent function is being vertically compressed by 1/2. It's a vertical compression or shrink by 1/2. And you have to be careful. The textbook, I'm not a fan of the textbook, this section in the textbook. I think that the way that the words that they use to describe the stretch or shrink factor does not go along with the definition that they give. So please make sure that you are following the way that I am describing a vertical stretch or compression. Again, I don't care if you use the word compression or compressed versus shrink or shrunk, but please stay consistent with everything else. And what happens here is we must multiply each y by 1/2. Which is also the same thing as dividing each y by 2 in this case, but we're gonna stick with multiplication. So we must multiply each y by 1/2 for the point to have the same x-coordinate as the parent function. So referencing the parent function again, 0, 0 would stay the same. However, 1, 1, when we multiply the y-coordinate by 1/2 would be at 1, 1/2. Okay, 2, 2 would end up at 2, 1. 3, 3 would end up at 3 and then 1/2 or 3/2. 4, 4 would end up at 4, 2, and so on. You also know from Algebra 1 that this is a line that has a y-intercept of 0 and a slope of 1/2. But try and think of it, at least for a few points, in graphing from the transformation perspective. Okay, so let's look at horizontally stretching or compressing. Again, you can use the word shrinking instead of compressing. Again, we're letting the parent function be f of x. So if x, or if the independent variable is multiplied by a constant, that is larger than 1, then that's actually going to horizontally compress the graph of the parent function. And the reason that is, I always have to think an extra second about anything that's horizontal, is that for the new graph to have the same y coordinate as the parent function, we would have to do the opposite, or we would have to multiply the input by the reciprocal of c in order to have the same y coordinate as the parent function. So you end up having to multiply by the reciprocal, each x by the reciprocal, in order to have the same output. So the words that we would use here is we would say f of x is horizontally compressed or shrunk by 1 over c, so whatever the reciprocal of c is. And that describes what you have to do to x. Remember, anything horizontal is happening to x, whereas anything vertical is happening to y. So we're describing what we actually end up having to multiply x by, and that is the reciprocal of c. And for horizontal stretch, we say f of x is horizontally stretched by 1 over c for that same reason. Describes what we are multiplying our inputs by. Again, y equals to x. I should have copied and pasted. Here, I'll just draw this quickly. Okay, so same equations as above, but instead remember how in when we were talking about shifts, how if I just added the parentheses, then I read the equation as being a horizontal shift instead of a vertical shift. So I'm going to do the same thing here. So if I take the equation y equals to 2x, but I read it in parentheses, then I would be reading that as the parent function is being horizontally compressed by 1/2 because the x is being multiplied by 2. Instead of thinking about it as being the parent function being multiplied by 2. So the way that this is written, what did I do? I was doing star. The parent function is being horizontal. This is a horizontal compression by 1/2. We have to think about multiplying each x from the parent function by 1/2 in order to have, we have to multiply each, x by 1/2 from the parent function in order to have the same y coordinate. Okay, 0, 0 ends up staying the same place. However, the point 1, 1, if I multiply x by 1/2, would end up being 1/2, 1. Okay, 2, 2 would end up being, when I multiply the x coordinate by 1/2, that ends up being at 1, 2. 3, 3 ends up at 3/2, 3. 4, 4 would end up at 2, 4, and so on. So 1, 1 would end up at, negative 1 would end up at negative 1/2 negative 1. Negative 2 would end up at negative 1 -2. And then we can just extend the line. And then if we had the equation y equals 2 in parentheses, x over 2, which is the same thing as 1/2 times x, but I'm putting in parentheses so that it represents a horizontal stretch. We would say that there's a horizontal stretch by 2 to the parent function. Which means we must multiply each x by 2. So 0, 0 stays where it is. 1, 1 would end up at 2, 1. Okay. 2, 2 would end up at 4, 2. 3, 3 ends up at 6, 3. 4, 4 ends up at 8, 4. 5, 5 would end up at 10, 5. And then negative 1 would end up at negative 2, 1. Negative 2 would end up at negative 4, 2. Negative 3 ends up at negative 6, 3. And so on. So I'm aware you guys know how to graph these lines already. I'm just trying to show you how you can think of graphing them from a transformation perspective. So horizontal stretch or compression, or with a vertical stretch or compression. Okay, so let's look at some other examples. So the parent function for f of x would be x squared. So I'm thinking about that parent function x squared that has points at 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. So I'm going to be thinking about transforming those points. Now there's no parentheses. This is 3 times x squared. So that's like 3 times the parent function. Meaning this is a vertical, that 3 represents a vertical stretch by 3. Meaning we are going to multiply each y by 3. Okay, so 0, 0 would stay the same. 1, 1 would end up at 1, 3. Negative 1, 1 would end up at negative 1, 3. 2, 4 would end up at 2, 12. So it would be off of the graph. It would be like up here. And negative 2, 4 would end up at negative 2, 12 and would be off of the graph. So you can see the graph ends up being skinnier looking from it being vertically stretched. Okay, the parent function for g is y equals to the cube root of x, right? That's the sideways chair function. So I'm thinking about the point 0, 0, 1, 1, negative 1, negative 1. Now notice that this 2 is underneath the cube root. So x is being multiplied by 1/2. This can also be written as the cube root of 1/2 times x. So this is a horizontal stretch by 2. I knew it was horizontal because it's happening to the x. And we use the reciprocal to describe what's happening. So all of the x's for the parent function are being multiplied by 2. So 0, 0 stays where it is. 1, 1 would go to 2, 1. Negative 1, negative 1 would go to negative 2, negative 1. Let's think. 8, 2 is another point on the parent function. So, that goes way off of the graph. 16, 2 would end up being the next points that we're familiar with. Okay, so this is the cube root of x stretched horizontally by 2 to give us g of x. Okay, the parent function for h of x is absolute value of x. Right, the v has its point at the origin. And then 1, 1, 2, 2, 3, 3, 4, 4. Negative 1, 1, negative 2, 2, negative 3, 3, and so on. That 2 is on the inside of the absolute value bars. So x is being multiplied by 2. That means that this is a horizontal compression or shrink. Can use either term by 1/2. And that's because we multiply each x of the parent function by 1/2. So 0, 0 stays where it is, but 1, 1 would end up at 1/2, 1. Negative 1, 1 would end up at negative 1/2, 1. 2, 2 would end up at 1, 2. Negative 2, 2 would end up at negative 1, 2. 3, 3 would end up at 1.53 or 3/2, 3. And negative 3, 3 would end up at negative 3/2, 3. 4, 4 would end up at 2, 4. Negative 4, 4 would end up at negative 2, 4, and so on. So you can see that's horizontal compression. So I always think of a slinky when I think about horizontal and vertical stretch and compression. So the graph has been horizontally compressed, which actually ends up looking like also a vertical stretch in this case. However, the way the equation is written, it is written as being a horizontal compression. Okay, so let's look at a few examples where there's a combination of translations and transformations. So some shifts as well as stretch or shrink, or maybe even some reflections. So for f, our parent function is y equals to x squared. So I know what parent function I'm visualizing right now and what points I'm thinking about. That 2, I'm going to write down the translations and transformations in order. The first one is from that 2. So that 2 is actually a vertical stretch by 2. Which means all the y coordinates for the parent function are being multiplied by 2. And then that minus 1 is a horizontal shift to the right 1. So the point 0, 0, when stretched by 2, nothing would happen. It would stay at 0, 0. But then shifting to the right 1 would be at 1, 0. The point 1, 1, when vertically stretched by 2, would go to 1, 2. And then I need to shift to the right 1 to land me at 2, 2. The point negative 1, 1, when vertically stretched by 2, would put me at negative 1, 2. But then when I shift to the right 1, that lands me at 0, 2. 2, 4, when vertically stretched by 2, would land me at 2, 8. But then shifted to the right 1 puts me at 3, 8. And negative 2, 4 would put me, when vertically stretched, would put me at negative 2, 8. And then shift right 1, I'm at negative 1, 8. And I'll switch colors. We'll go orange for g of x. Now g of x has to be rewritten. Remember how I mentioned this in the last video. If anything is happening, if x is being multiplied by anything other than positive 1, you need to, and there's a horizontal shift, you need to factor out whatever x is being multiplied by in order to see the actual horizontal shift. So in this case, we would actually want to factor out negative 2 underneath the radical, which would leave us with negative 2 times the quantity x minus 3. Our parent function is y equals to the square root of x. Doesn't look like anything vertical is happening to the parent function. There's no vertical stretch, compression, reflection. But there is a negative underneath the radical. That indicates a horizontal reflection. That 2 indicates horizontal compression by 1/2 or horizontal shrink by 1/2. And then the minus 3 is a horizontal shift to the right 3. So I'm going through the points that I'm familiar with from the parent function. I'm going through this list with each of those points. So the point that's at 0, 0, horizontal reflection, it doesn't go anywhere. Horizontal shrink doesn't do anything. Horizontal shift to the right 3 lands me at 3, 0. 1, 1. When applying the horizontal reflection lands me at negative 1, 1. The horizontal shrink then lands me at negative 1/2, 1. And then when I shift to the right 3, 1, 2, 3, that lands me at 2.5, 1. For 2 on the parent function, horizontal reflection lands me at negative 4, 2. The horizontal shrink by 1/2 lands me at negative 2, 2. And then I go right 3, 1, 2, 3, landing me at 1, 2. The 3 points are fine. I'm just going to do that last point from the parent function that I know would fit in this graph. So 9, 3, horizontal reflection lands me at -9, 3. Horizontal shrink by 1/2 would land me at -4.5, 3. And then right 3, 1, 2, 3 would land me at -1/2. Sorry, -1.5, 3. The parent function for h of x is absolute value of x. I'm going to rewrite that equation, although I think it's probably pretty obvious to you that there's a horizontal stretch by 2. I'm going to rewrite that equation as the absolute value of 1/2 times the quantity x minus 1, just in case you didn't see it. So just reading the equation from left to right to identify what's happening. And by the way, I don't have any vertical shifts on here, but I always apply the vertical shifts last. That 1/2 is a horizontal stretch by 2. And then the -1 is a horizontal shift to the right 1. So I'm thinking about the parent function. 0, 0 wouldn't go anywhere from the stretch. We shift to the right 1, landing me at 1, 0. 1, 1, when horizontally stretched by 2, lands me at 2, 1. But then I shift to the right 1, landing me at 3, 1. -1, 1, when horizontally stretched by 2, puts me at -2, 1. I shift to the right, and I'm at -1, 1. 2, 2, horizontal stretch, lands me at 4, 2. Right 1 lands me at 5, 2. And then -2, 2, when horizontally stretched, lands me at -4, 2. And then right 1 lands me at -3, 2. So that would be the graph of h. So because I didn't put a vertical shift on here, I am going to give one additional example. How about cube root? So let's do t of x equals to, 2 times the cube root of x plus 1, or we'll do x plus 2. And then how about minus 3? So reading from left to right, let me choose color. Oh, my parent function would be the cube root of x. And that 2 would be a vertical stretch by 2. The plus 2 underneath the cube root would be a horizontal shift left 2. And then the minus 3 on the outside would be a vertical shift down 3. Ooh. So the point that was at 0, 0, that vertical stretch, it would stay at 0, 0. Horizontal shift left 2 puts me at negative 2, 0, and then down 3 would put me at negative 2, negative 3. The point that would be at 1, 1 on the parent function, vertical stretch puts me at 1, 2. Horizontal shift left 2 would put me at negative 1, 2, and then down 3 would put me at negative 1, negative 1. The point that's at negative 1 on the parent function, vertical stretch would put me at negative 1, negative 2. Horizontal shift left 2 would put me at negative 3, negative 2, and then down 3 lands me at negative 3, negative 5. Okay. How about the point that's at 8, 2 on the parent function? Would land me at 8, 4 for the vertical shift. Left 2 lands me at 6, 4. And then down 3, 1, 2, 3, would land me at 6, 1. Negative 8, negative 2, when stretched by 2, would land me at negative 8, negative 4. And then I go left 2 to be at negative 10, negative 4, and down 3, 1, 2, 3, lands me at negative 10, negative 7. And I called that T of X. So my warning is just beware if a vertical shift, which sometimes you'll see this, so warning, or watch out. If you see a vertical shift written first, like let's say you had y equals to 3 minus 4 times x minus 1 squared. I would rewrite that before you list or think about what translations and transformations are happening as negative 4 times x minus 1 squared plus 3. And if you do that, then you can think about the shape being changed. So whether there's a stretch, compression, or a reflection before you actually shift horizontally or vertically. So basically the shifts happen last, after the shape or any reflections have been applied.